Imagine, just for a second, that you're designing a state-of-the-art fire protection system for this massive industrial complex.
Oh, the classic high-stakes scenario.
Right. You've spent weeks meticulously calculating every single sprinkler head's flow rate. You've optimized the pipe routing to minimize friction loss. You've accounted for every single elbow and tee.
Down to the last decimal.
Exactly. And you've specified the absolute best, most efficient centrifugal fire pump on the market. The engineering on your desk is just completely flawless.
On paper, at least.
On paper, yeah. But then, a fire breaks out in the facility. The heat detectors trip, the system kicks on, and it completely fails.
It's almost never the pump itself that fails in that situation.
No, it fails because of something like a localized invisible velocity gradient in the water supply tank that induces a vortex. Or maybe a single discharge elbow experienced catastrophic thermal stress overnight.
Because it froze.
Right. As a safety engineer, you know this harsh reality. The water source is your foundational failsafe. If that water supply goes down, the entire meticulously designed system downstream is just an incredibly expensive network of, well, useless metal.
Yeah, that failure isn't theoretical. It is the ultimate nightmare scenario in fire protection engineering, and I mean, it happens.
It really does.
You can have the most advanced hydraulic distribution network in the world, but it entirely relies on the fundamental assumption that water will just be there at the required pressure in the necessary volume, the exact millisecond that impeller starts spinning.
And when engineers treat the water tank as just a static bucket rather than a dynamic engineered machine, that's when those critical failures occur.
Precisely, which is why the NFPA completely rewrote several critical rules in the 2023 edition of NFPA 22.
Yeah, the standard for water tanks for private fire protection.
Hmm.
And today, this deep dive is custom tailored for you, the safety engineer.
We're going to strip away the dense regulatory jargon.
Exactly. We want to look at the raw physics of why these water systems fail and how to engineer them correctly. We're exploring the fluid dynamics, the thermodynamic load limits, and the specific mechanical failsafes.
The things that make these regulations absolutely necessary for your daily design work. We are pulling actionable design principles directly from the official 2023 text.
Yeah, because this document covers the design, construction, installation, and maintenance of, well, pretty much everything. From gravity tanks sitting on 100-foot structural steel towers to pressure tanks, suction tanks, brake tanks.
Even coated fabric tanks.
Yeah. Our goal today is to bridge the gap between the code book and your CAD software. So I want to start with the foundational philosophy of the water supply itself.
That's section 4.2.1, right?
Yeah, section 4.2.1. It lays down a very strict legal and engineering baseline. It explicitly states that the adequacy and dependability of the water source is of primary importance.
But, I mean, what does primary importance actually mean when you're sitting down to design a system from scratch?
That's the question.
It means the NFPA committee is explicitly warning engineers not to make assumptions about municipal infrastructure. If the city water isn't adequate, whether that deficiency is in quality, quantity, pressure, or just historical reliability, you have to engineer an alternative.
A dedicated source.
Yeah.
You can't just specify tap into a city main, run your hydraulic calculations based on, like, a single flow test performed on a random Tuesday morning and call it a day.
No, the standard requires proof of dependability.
Which brings us to a really critical design component, the brake tank. If you look at Annex ATOT 14.5, it outlines exactly why and when an engineer would specify a brake tank.
There are three primary functions listed there: preventing backflow into the city supply, eliminating pressure fluctuations, and augmenting an inadequate city supply.
Right, so let's look at the mechanics of the first one. Backflow prevention seems pretty straightforward, but what is the actual physical mechanism we're engineering here?
The physical mechanism is simply an air gap.
An air gap.
Yeah. If your fire pump is pulling a massive amount of suction, say 2,500 gallons per minute, it creates a severe low-pressure zone.
A huge vacuum.
Exactly. And if a city water main were to break simultaneously, or if the municipal pumps failed, the pressure in the city grid could actually drop below atmospheric pressure.
Oh, wow. So without a physical break, your fire pump could essentially suck stagnant or chemically treated water backwards.
Right, from your private industrial fire system directly backward into the public drinking water supply.
That would be a disaster.
A massive public health hazard. So a brake tank prevents this by terminating the municipal fill line above the highest possible water level of the tank. The water falls freely through the air into the tank. You physically cannot siphon backwards across an air gap.
Okay, so the brake tank is physically severing the hydraulic connection. I get that. Now, the second reason, eliminating pressure fluctuations, that requires a bit more mechanical analysis.
It does.
I look at a brake tank kind of like an electrical capacitor in a circuit, or maybe a massive battery buffer in a local power grid.
That's a great analogy.
Because you have this chaotic, wildly fluctuating pressure coming from the city grid, right? It's subject to domestic demand spikes, main breaks, municipal maintenance.
All those variables you can't control.
Exactly. So you dump that water into the tank, completely stripping away its pressure energy.
Yeah.
You smooth it out, so you deliver a steady, reliable, totally predictable flow to the fire pump.
Based solely on the static head of the water in the tank.
Right.
And that electrical capacitor analogy holds up really well under fluid mechanics. A fire pump is a highly tuned piece of rotating equipment. It's engineered to perform on a very specific pump curve.
So if the input is jumping all over the place,
The output will too. If the suction pressure feeding that pump is constantly spiking and dropping, the pump's discharge pressure will oscillate violently.
which causes hydraulic transients.
Water hammer. And that shock wave travels throughout the entire downstream sprinkler system, potentially blowing out fittings or sprinkler heads before the fire even reaches them.
So the brake tank guarantees a consistent, predictable suction pressure. It decouples the pump's performance from the chaos of the municipal grid.
Exactly. And the third reason is volume augmentation. If the city infrastructure can only deliver, say, 500 gallons per minute due to pipe friction or sizing.
But your specific hazard analysis demands 1,500 gallons per minute?
Right. Then the brake tank makes up that massive deficit.
Okay, but I want to push back on this entire premise for a second. Let's say you're engineering a facility in a major metropolitan hub. New York, Chicago, London.
Okay.
There are massive 36-inch municipal water mains right under the street. The volume is practically infinite. Why would any engineer justify adding the immense capital cost, the real estate footprint, and the perpetual maintenance of a massive private brake tank?
When they have a century of city infrastructure at their doorstep.
Yeah. Facility owners will definitely argue against that to cut costs.
Oh, they absolutely will. But as the safety engineer, your responsibility is risk mitigation. And municipal infrastructure is a massive, uncontrollable variable.
But it's old.
Partly, yes. Those 36-inch mains in major cities are often 80 to 100 years old. They're cast iron, they're brittle, and they fail catastrophically.
That makes sense.
Plus, municipalities constantly reroute water, throttle valves, or lower system-wide pressures to reduce leakage rates in their aging pipes.
So the pressure you measured last year might not be there today.
Exactly. If you tie your life safety system directly to that grid without a buffer, you are inheriting 100% of their hidden vulnerabilities. A private tank isolates your facility from external failures. You're buying control over your own hydraulic destiny.
Control over the variables. I like that. And if we look at section 4.2.1.4, there's a very strict design parameter enforcing that control. The standard requires that your water supply must be capable of filling the minimum required fire protection volume in a maximum of 8 hours.
That 8-hour rule fundamentally alters how you design the fill line.
It's not just an arbitrary number, is it?
Yeah, not at all. It means you have to mathematically prove that after a full-scale fire event or after a massive system drain from maintenance, the facility can be fully armed and ready to fight a second independent fire within a single standard working shift.
Let's run the math on that to see the scale.
Yeah.
If you specify a 300,000-gallon private water tank, filling that in 8 hours requires a constant flow rate of 625 gallons per minute.
Which is massive.
Right. That isn't just a domestic water line. That requires a dedicated, heavily engineered municipal tap, specialized backflow preventers, and a massive control valve array just for the refill mechanism.
And you have to guarantee the city can even provide that 625 GPM continuously for 8 hours without dropping pressure to the surrounding neighborhood.
Exactly. The refill mechanism requires as much hydraulic engineering as the discharge system.
And if your calculations show the fill line is too small to achieve that 8-hour window, the design is legally non-compliant.
Period.
Period. Furthermore, if the tank is not at its sufficient calculated capacity at any point, the standard triggers the impairment procedures outlined in NFPA 25.
Which means what, practically?
You essentially have to declare the fire protection system compromised. That can force a facility to halt operations, institute continuous fire watches, and notify insurance carriers. The 8-hour rule is a massive operational constraint.
So we've established the mechanics of standing, unpressurized water. Let's transition to a completely different physical state. Chapter 7 covers pressure tanks.
Moving from gravity-fed systems and atmospheric brake tanks to pneumatic power.
Right. These tanks use compressed air to violently expel the water into the piping network.
A pressure tank is a localized high-energy vessel. The standard is extremely rigorous regarding their design because you aren't just holding static water.
You're holding a mathematically calculated ratio of air to water.
Exactly, and you're compressing it under significant pressure. It's essentially a loaded mechanical spring.
The mechanism reminds me of a heavy-duty industrial-scale super soaker.
That is exactly what it is.
You pump in the compressed air, and that air acts as the stored kinetic energy. When a sprinkler head pops due to a fire, the compressed air expands, shoving the water through the pipe network.
And the engineering brilliance here is that it requires absolutely zero electricity or mechanical pumping during the actual fire event.
It's a completely passive delivery mechanism once it's pressurized.
It is, but the mathematics required to design it are pretty unforgiving. Annex A. and 7.1.4.2 details the physical calculations. You're utilizing Boyle's law.
The principle that the pressure and volume of a gas have an inverse relationship.
Right. You have to ensure that the volume of compressed air in the tank and the initial pressure it's placed under is sufficient to push every single required drop of water out of the tank.
While still maintaining residual pressure.
Exactly. You must maintain the necessary residual operating pressure at the highest sprinkler head in the building at the very end of the discharge cycle.
Let's break that down, because the variables are tricky. If the air pressure drops to zero, while there is still, say, 500 gallons of water sitting in the tank, that water is dead weight.
Completely dead weight. It will just sit in the basement while the roof burns.
So how does an engineer physically calculate that initial pressure and volume requirement?
You work backwards from the hydraulic demand.
Yeah.
First, you calculate the pressure and flow required at the most remote sprinkler head.
Okay, the furthest point in the system.
Right. Then you calculate the friction loss through the entire piping network all the way back to the discharge flange of the pressure tank. That gives you your final required pressure.
Got it.
But here is the critical step. You must select a physical tank volume that is significantly larger than your actual water demand. You need that extra empty volume to hold the compressed air.
And then you use the ideal gas loss.
Exactly. Once you have your total volume and your water volume, you calculate the starting pressure required to achieve that final discharge pressure.
But there's a massive engineering constraint hidden in that calculation. What happens if your math dictates you need a starting pressure of, let's say, 200 psi to push all the water out?
Then you have a major conflict with your downstream component.
Because they can't handle that pressure.
Right. If the holding pressure required in the tank exceeds the maximum pressure rating of the other components in your fire protection system, like the butterfly valves, the alarm check valves, or the sprinkler heads themselves.
Which are often only rated for, 175 psi?
Usually 175 psi, yes. If your tank needs 200 psi, you cannot build the system. You cannot intentionally overpressurize the downstream network.
So what is the solution? If the math requires 200 psi, but the valves can only handle 175 psi, how do you resolve that as the designer?
You're forced to manipulate the volume variable in Boyle's law. The standard dictates that the engineer must select a physically larger tank.
Oh, I see.
A larger overall tank, holding the exact same amount of water, means you have a much larger volume of compressed air.
And because you have more air volume, it doesn't have to expand as much to push the water out.
Exactly. Therefore, you can start at a much lower initial pressure to achieve the exact same final expulsion force.
You are trading physical space, specifying a massive steel vessel that eats up mechanical room square footage in order to lower the required operating pressure to safe levels.
That is the fundamental engineering compromise, trading spatial footprint for pressure reduction.
And regarding those massive steel vessels, the manufacturing and testing requirements are incredibly intense. The standard requires they be hydrostatically tested to at least 150 psi.
And they must hold that pressure without dropping more than 0.5 psi over a full 24-hour period.
That is an extremely tight tolerance,
Yeah.
practically zero allowable leakage.
Because a slow pneumatic leak over 6 months means the system is entirely dead when a fire breaks out. But engineers need to be really aware of the thermodynamics during that 24-hour test.
How so?
Well, according to Gay-Lussac's law, the pressure of a gas is directly proportional to its absolute temperature.
Temperature fluctuation.
Right. If you pressurize the tank on a hot afternoon and the mechanical room temperature drops 15 degrees overnight, The pressure in the tank will drop simply due to the air cooling and contracting.
So an engineer or inspector who doesn't account for temperature differentials might fail a perfectly sealed tank.
Or worse, pass a leaking tank if the room heated up and masked the pressure loss.
Thermodynamics impacting hydrostatic testing. That is exactly the level of detail safety engineers need to consider. Now, there is another tiny, highly specific detail regarding the pressure tank's nameplate.
Section 7.1.8.2.
Yeah, it requires a metal nameplate with raised or stamped letters showing the manufacturer, year, capacity, and working pressure. But Section 7.1.8.3 mandates that this nameplate must also serve as the actual water level indicator.
Bearing an easily observed raised arrow.
Right. Why mandate a raised metal arrow on a riveted plate? Why not just paint a fill line on the side of the tank or use a heavy-duty industrial sticker?
Because the NFPA operates on a timeline of decades. Paint fades, chips, and degrades. Industrial adhesives fail in the constantly damp, fluctuating environment of a mechanical room.
So it has to be permanent.
A raised metal arrow, physically stamped into a riveted plate, is infallible. When a maintenance technician walks into that room 15 years after you designed it to verify the water-to-air ratio, they need an unalterable reference point.
Because if they get the ratio wrong,
The physics fail. If they fill the water too high, there isn't enough room for the air, and the tank won't fully discharge. If they fill it too low, you don't have enough water to fight the fire. That raised arrow is a microscopic detail that guarantees the macroscopic physics of the tank remain accurate for half a century.
the code is essentially forcing longevity into the physical hardware. Okay, let's move from static and pneumatic pressure into the realm of water and rapid motion. I want to dive deep into fluid dynamics, specifically Section 9.6.2.3.
Vortexes and cavitation.
Yes, we established earlier that a vortex can destroy a pump. But let's break down the actual fluid mechanics of why a whirlpool in a tank is so lethal to a system.
When a massive centrifugal fire pump activates, it generates a tremendous velocity at the suction inlet pipe, which is usually located at the bottom of the tank.
Right?
As the water level drops, the fluid velocity gradient changes. If the rotational flow of the water is not controlled, a vortex forms.
The common, explain it like I'm five analogy is the bathtub drain. You pull the plug, the water swirls, and you get a funnel of air sucking down the middle.
Exactly like that.
But in a bathtub, it just makes a gurgling sound. In an industrial fire protection system pulling thousands of gallons a minute, we're dealing with complex throated numbers and sheer fluid stress.
And if that vertical funnel of air reaches the pump inlet, you induce cavitation.
Let's define cavitation for the listeners, because it's not just air in the pump.
No, cavitation is the mechanical destruction of the pump. It occurs when the pressure inside the pump impeller drops below the vapor pressure of the water.
But in this vortex scenario, we are forcefully injecting air bubbles directly into the low-pressure suction side of the pump.
Right. And as those entrained air bubbles pass through the spinning impeller and hit the high-pressure discharge side, they cannot sustain their structure, they collapse violently, they implode.
The micro-implosions.
Yes. And the shock waves from those microscopic implosions generate immense localized stress. They literally blast microscopic pits into the solid bronze or stainless steel of the impeller blades.
Oh, wow, so it's physically eating away the metal.
It sounds like a handful of gravel has been thrown into the pump casing. Within minutes, cavitation will erode the impeller to the point where it can no longer generate the required discharge pressure.
So the pump is running, the motor is screaming, but no water is reaching the fire.
A total system failure.
So the engineering challenge is, how do you stop a vortex from forming in a tank holding hundreds of thousands of gallons of moving water?
The standard mandates a vortex plate assembly, often called an anti-vortex plate. It has to be bolted to the combination inlet-outlet fitting.
You essentially hover a massive coaster over the drain.
That's a great visual. And if you examine the specific diagrams in Annex B, specifically Figure B1P, the dimensions are rigid.
What are we talking about here?
A standard vortex plate is typically a 48-inch by 48-inch square of heavy steel, and it must be placed not less than 6 inches above the bottom of the tank.
Let's analyze those dimensions, because an engineer might look at a 4-foot steel plate inside a tank and think, well, that's overkill. Why mandate 48 inches wide, and why exactly 6 inches off the floor?
It is about forcefully manipulating the fluid velocity vectors. By placing a massive flat barrier directly above the suction pipe, you physically block the vertical air funnel from reaching the pipe.
You force the water to change direction.
Exactly. The pump must now draw water horizontally from the outer edges of the plate, parallel to the tank floor, rather than vertically from the surface. This horizontal shear cuts off the rotational energy required to sustain a vortex.
Okay, that makes sense for the width, but what about the 6-inch height? Why not bolt it 2 inches off the floor to get every last drop of water, or maybe 24 inches off the floor to ensure a maximum flow area?
It's a highly engineered balance of fluid dynamics. If you mount the plate 24 inches high, you create 2 feet of dead water below the plate.
Because the pump is pulling from above the plate.
Exactly. Once the water level drops to the top of the plate, the pump starts sucking air, rendering the remaining 2 feet of water completely unusable. In a massive tank, that could be tens of thousands of gallons of water wasted.
Right, and if you mount it too low?
Say 2 inches off the bottom. The cross-sectional area between the edge of the plate and the floor becomes so small that you induce massive friction loss. The fluid velocity skyrockets, the pressure drops, and you starve the pump.
Which again causes cavitation.
6 inches is the mathematically proven sweet spot. It provides enough cross-sectional area for the water to flow horizontally without starvation, while minimizing the volume of dead water left at the bottom.
That is a perfect example of a static piece of metal solving a highly complex dynamic fluid problem. And, the 2023 edition actually updated the tank sizing requirements to ensure that these fluid dynamics are considered even earlier in the design phase.
Yes, they introduced specific separation distances.
Between the fill lines dumping water into the tank and the suction pipes pulling water out.
That was a much-needed addition to the code. Think about it. If your fill line is dumping a high-velocity stream of fresh water directly above or immediately adjacent to your suction pipe, that incoming column of water creates severe turbulence.
It's churning everything up.
It introduces millions of entrained air bubbles deep into the water column, and if the downward velocity of the pump suction is greater than the natural upward buoyancy velocity of those air bubbles,
The pump will just inhale that air.
which leads right back to cavitation and pump destruction, even without a vortex.
So the new standard forces safety engineers to spatially separate the incoming and outgoing pipes. You have to give the incoming water enough physical distance and time to decelerate, calm down, and allow the entrained air bubbles to naturally float to the surface.
Before that water reaches the suction inlet, you are literally managing the internal currents of the tank.
A tank is essentially a controlled hydrodynamic ecosystem. Okay, let's shift away from the water inside the tank and look at the structure holding it up. Section 4 focuses on protecting the protector fireproofing and structural integrity.
Section 4.3 outlines the location of tanks. It clearly states that if a tank is located close to a building or a fire hazard, the supporting steelwork must be protected from fire exposure.
Now, this concept frequently catches junior engineers off guard. The immediate instinct is to ask, why do I need to fireproof a water tank? It's a massive heat sink filled with hundreds of thousands of gallons of cold water.
It's a fair question, but the water only protects the thin steel shell of the tank itself. It does absolutely nothing to protect the structural steel tower supporting that tank 100 feet in the air.
We are dealing with massive, exposed steel columns. And to understand why this is a code requirement, we have to look at the metallurgical properties of steel under thermal load.
Right. Structural steel, like the common STM A30 used in heavy construction, has incredible yield strength at ambient temperatures. But as it heats up, its crystalline structure begins to change.
How hot does it need to get?
Once steel reaches roughly 1,000 degrees Fahrenheit, which, by the way, is a temperature easily achieved in a standard commercial fire, it loses roughly 50% of its load-carrying capacity.
It doesn't melt, though.
No, it softens and yields.
And the dead load we're talking about is staggering. Water weighs roughly 8.34 pounds per gallon. If you design a 100,000-gallon elevated gravity tank, you have over 830,000 pounds of water, plus the weight of the steel itself sitting high in the air.
So if a fire breaks out at the base of the tower,
Say, a pallet storage fire in a loading dock, or a fuel spill from a vehicle.
and those steel legs reach 1,000 degrees, the columns will buckle under the immense vertical load. It will be a catastrophic structural collapse.
You instantly lose your entire primary water supply, completely neutralizing your fire protection system right when it is needed most.
Not to mention, dropping 1 million pounds of steel and water onto the facility creates a massive lethal secondary disaster for the building occupants and the first responders.
Which is why the standard strictly mandates a fire resistance rating of not less than 2 hours for the fireproofing of those supports, or they must be protected by a dedicated open sprinkler system.
And Annex 813.1.1 actually provides a highly specific, robust method for achieving that fireproofing on steel columns.
Yeah, the text suggests pouring a minimum of 2 inches of concrete outside all the projecting steel. But there's a very specific caveat. To keep the concrete in place, you must spirally wind the steel column with number 5 B&S gauge steel wire before pouring.
That's a crucial detail.
What is the mechanical purpose of that specific wire gauge inside the concrete?
It addresses the physics of concrete spalling under extreme heat. Concrete contains trapped moisture within its capillary matrix.
Right, it's never completely dry.
Exactly. During a severe fire, when the face of the concrete hits 212 degrees Fahrenheit, that trapped moisture instantly boils into steam. And water expanding into steam increases in volume by roughly 1,700 times.
That's a massive expansion.
This rapid expansion creates immense internal pressure that physically blows chunks of concrete off the steel column that's spalling.
So the concrete essentially detonates itself.
Yes, and once it spalls, the bare steel is exposed to the flames. The heavy No. 5 B&S gauge steel wire acts as a structural containment cage.
Even as the concrete cracks.
Even as it cracks and the moisture boils off, the wire mesh holds the aggregate matrix tightly against the steel column, ensuring the insulative thermal barrier remains intact for the full 2-hour rating.
It is a brilliant brute force engineering solution. The standard is also uncompromising regarding what materials you can use for support. It explicitly forbids the use of interior timber to support or brace these tank structures.
You cannot have hidden combustible framing inside the structural envelope.
And if an engineer plans to mount a gravity tank on the roof of a building, which is, the standard approach in dense urban environments like Manhattan,
the building's structural frame must be specifically engineered to carry those maximum loads, and roof mounting introduces severe dynamic engineering challenges.
because it's not just static weight anymore.
Right. You aren't just calculating the static dead load of the water, you must calculate the dynamic sloshing loads.
Swashing loads.
If a seismic event occurs, or even extreme wind loads, that massive body of water begins to oscillate. The momentum of 100,000 gallons of sloshing water creates immense lateral shear forces.
That could rip a tank off its mounts.
Or severely compromise the building's structural integrity. The tank must be engineered with internal baffling to break the momentum, and the building must be rated for that massive seismic mass participation.
Okay, so we've protected the system from fire and gravity. Now we have to protect it from the opposite, extreme absolute zero. Section 5 of our outline covers environmental threats, specifically focusing on the battle against freezing, detailed in chapters 15 and 16.
A frozen system is a dead system.
Period.
Whether it's a 2-foot layer of ice on the surface of the tank preventing the float valves from operating, or a single frozen 90-degree elbow in the discharge pipe blocking flow, ice renders the entire fire protection system utterly useless.
And the 2023 edition introduced a massive paradigm shift in how engineers must approach frost design.
It really did.
For decades, the standard relied on a fixed, lowest one-day mean temperature map. An engineer would just look at the map, locate their county, read the historical temperature curve, and specify a heating solution based on that single data point.
But the 2023 update completely removed this map from the code.
They threw it out entirely in favor of dynamic, hard calculations to determine heating needs. Why the sudden shift away from historical data?
Because historical climate data is no longer a reliable predictor of future thermal extremes. We are routinely seeing deep, prolonged freezes in southern regions that historically never worried about severe frost, and extreme temperature fluctuations in northern regions.
So the map was obsolete.
By removing the static map, the NFPA is forcing the design engineer to actually perform transient heat transfer calculations. You must calculate the specific thermal loss of the tank based on its geometry, its material, the thickness of its insulation, and current localized meteorological data.
You use Newton's law of cooling.
Exactly. To determine exactly how fast the BTUs will bleed out of the steel and size your heating system to replace them.
It requires significantly more math from the engineer, but it results in a far more resilient design. Let's look at the mechanical solutions for stopping the pipes from freezing. The standard requires frost-proof casings for the vertical pipes running up the structural tower.
The easiest way to visualize this is like a highly engineered industrial thermos.
You build a concentric enclosure around the pipe and pack it with insulation to trap the residual heat of the water and the radiant heat from the earth.
But there's a critical, almost ironic thermodynamic twist that safety engineers must design into that vertical thermos.
What's that?
Section 15.2.2.2 requires that these frost-proof casings must have fire stops placed inside the casing at roughly 6 feet and 10 feet above the base.
These fire stops are horizontal layers of tightly packed, non-combustible insulating material that block the vertical air cavity.
Yes, and this is where understanding fluid mechanics meets fire dynamics. You build this highly insulated vertical tube specifically to keep the cold air out.
But if a fire starts at the base of the tower,
That vertical insulated tube will act exactly like a chimney. The heat will enter the bottom, and convective drafts will pull that superheated air straight up the pipe casing, accelerating the fire, melting the insulation, and potentially boiling the water inside the discharge pipe.
or destroying the tank connections 100 feet in the air.
The fire stops plug the cavity, breaking the chimney effect. You are designing against the cold, but the code forces you to remember that the primary overriding threat is always fire.
That is fascinating. Moving into the tank itself, Chapter 16 covers the specific heating equipment. There are new, highly stringent criteria for electric immersion heaters. If an engineer specifies an immersion heater, the standard mandates a recording thermometer.
But the critical detail is the placement of the thermometer's bulb.
Right. It must be placed in the coldest water of the tank. It doesn't monitor the average temperature or the temperature near the heater elements. It must monitor the absolute worst-case scenario.
And to find the coldest water, you have to understand thermal stratification and the density anomaly of water.
The density anomaly.
Yeah.
Water is actually at its densest at approximately 39.2 degrees Fahrenheit.
Right. As it cools toward freezing, it becomes less dense and floats. But a bulk mass of cooling water against the uninsulated steel shell will sink and stratify.
The engineer must locate the thermometer precisely where that freezing water will accumulate. If that localized cold spot drops below 42 degrees Fahrenheit, alarms must trigger.
Beyond the state change of water into ice, engineers must account for the mechanical stress caused by these wild temperature swings. As the ambient temperature shifts from a freezing winter night to a blistering summer afternoon, the metal itself expands and contracts.
Figure B1 in the annex details a critical mechanical solution for this: the use of 4 elbow swing joints on the piping connections. Let's calculate the physical reality of that.
Okay.
If you take the coefficient of thermal expansion for carbon steel, and you have a 100-foot vertical discharge pipe exposed to a 100-degree temperature swing throughout the year, that pipe is going to physically grow and shrink by roughly 3/4 of an inch.
3/4 of an inch of linear expansion sounds small, but the forces generated by that thermal expansion are immense.
Right, because it's solid steel.
If that 100-foot pipe is bolted rigidly to the bottom of the steel tank and the pipe grows, it will generate thousands of pounds of upward force. It will literally shear the bolts, buckle the pipe, or rip the discharge fitting right out of the floor of the tank.
So how does the 4 elbow swing joint solve this?
By using 4 90-degree elbows arranged in a specific geometric configuration, you create a physical mechanical hinge in the hard piping.
Ah, hinge.
As the long vertical run of pipe expands and gets longer, those elbows pivot and rotate slightly on their threads or grooved couplings. They absorb the extreme torsional and bending stress of the expansion, translating the linear growth into rotational movement.
It isolates the tank connection from the movement of the pipe. You were using geometry to defeat the violent physics of thermal expansion. It's a brilliant detail.
It really is.
Let's pivot to Section 6, Material Science and Commissioning. Chapter 4 strictly limits your tank material choices to steel, wood, concrete, coated fabrics, and fiberglass reinforced plastic, or FRP. And Chapter 17 dictates the highly specific and very different testing procedures for each material. Let's start with wood.
The inclusion of wood in a modern engineering standard often provokes a strong reaction.
Absolutely, and I'm going to push back hard on this. We are engineering state-of-the-art life safety systems in the 21st century. We have advanced polymers, carbon fiber, titanium alloys, and incredibly resilient epoxy-coated steel.
I know where you're going with this.
Why would an engineer, under any circumstance, specify a wooden tank to hold hundreds of thousands of gallons of water in an industrial setting? Wood rots, it warps, it's vulnerable to insects, it leaks, and it requires highly specialized coopers to build. How do you even calculate the structural lifespan of a living, decaying material?
It sounds counterintuitive, I'll give you that. But wood possesses highly specific mechanical and chemical properties that make it superior to steel in certain niche applications.
Like what?
First, wood has an incredibly low thermal conductivity compared to steel. In a deeply cold environment, a 3-inch thick cedar or redwood tank acts as its own massive thermos. It requires significantly less heating energy to prevent freezing than a highly conductive 1/4-inch steel plate.
Okay, I can concede the thermal argument, but what about longevity?
That is where the chemical properties come in. Wood doesn't rust. In highly corrosive industrial environments, such as chemical processing plants, pulp mills, or coastal facilities exposed to heavy salt spray.
Airborne corrosives will eat through industrial epoxy and aggressively oxidize a steel tank.
Exactly, drastically shortening its lifespan. A properly engineered wood tank, built from specific rot-resistant heartwoods like redwood or western red cedar, is chemically inert to those oxidizers. In those specific toxic environments, wood will outlast steel by decades.
Wow. The old ways still hold up against the physics of corrosion, but the standard is completely unforgiving on how these tanks are constructed. Section 8.1.4.2 explicitly bans the use of secondhand lumber.
You cannot use reclaimed timber. The structural integrity of the cellular matrix must be virgin and verifiable.
And the commissioning process is entirely unique. According to the National Wood Tank Institute Bulletin S82, you have to fill the tank and let it sit under the supervision of a specialist for a full 48 hours to check for liquid tightness.
Because you cannot test a wood tank immediately. The material has to adapt. Wood is hygroscopic.
It absorbs water.
The cellular structure of the staves needs time to physically absorb the water, swell, and expand. That swelling action creates immense compressive force between the joints, naturally sealing the tank. It is an organic mechanical seal.
And concrete exhibits a similar, though less organic, commissioning quirk regarding moisture absorption, right?
Yes, concrete is heavily regulated in the standard. When you commission a newly poured concrete tank, the testing protocol requires you to fill the tank to the brim, and then you are legally required to just walk away and let it sit for a full 24 hours without taking a single measurement.
Why is that? Because dry concrete is fundamentally porous. It contains a vast microscopic capillary matrix. When you introduce hundreds of thousands of gallons of water, the concrete physically drinks it. It absorbs the water deep into its structure.
Right. And if an engineer or inspector began measuring the water level immediately upon filling, the drop in volume would be so rapid it would simulate a massive structural leak.
You'd panic and think the foundation was cracked.
Exactly. You must allow the concrete to saturate for 24 hours to achieve hydraulic equilibrium. Only after the matrix is fully saturated do you begin the actual 72-hour test to measure for genuine volume loss and verify true liquid tightness.
It's crucial to understand the material's behavior to avoid a false failure during commissioning. The final material I want to analyze is fiberglass reinforced plastic, FRP.
FRP is lightweight, strong, and highly corrosion resistant.
But the NFPA rules regarding FRP are heavily focused on where you place the tank, primarily due to fire dynamics. If you install an FRP tank inside a building, the standard mandates it must be protected by automatic sprinklers, specifically engineered to ordinary hazard group 2 or OH2 requirements.
The challenge with FRP is the chemical composition of the resins used to bind the fiberglass. Unlike steel or concrete, which are non-combustible, many FRP resins will burn.
Even the fire retardant ones.
Even the fire retardant resins will lose their structural integrity rapidly when exposed to the high heat flux of a room fire. If the ambient heat softens the resin, the tank will burst and you instantly lose your water supply.
The ordinary hazard group 2 requirement dictates a specific heavy density of water spray to suppress the room fire and cool the tank surface before it reaches its critical failure temperature.
Furthermore, if you specify a horizontal FRP tank that is over 4 feet in diameter and you position it 18 inches or more off the finished floor, it triggers specific obstruction rules.
The umbrella effect.
Yes, it acts as a massive umbrella. If a fire starts underneath that suspended horizontal tank, say, a pile of oily rags or a pump motor catches fire, the ceiling-mounted sprinklers cannot reach the flames.
The massive footprint of the tank blocks the downward water spray, creating a dry shadow. The fire will grow unobstructed beneath the tank, directly heating the FRP material.
Therefore, the engineer must design an entirely separate array of sprinkler heads underneath the tank to protect that shadow area. Every spatial decision in fire protection creates a cascading series of hydraulic requirements.
Everything is mechanically interconnected. It's fascinating. Let's move into our final technical segment, Section 7 of the outline. We're looking at Section 11.7, which governs tanks utilized as cisterns.
This is a critical departure from everything we've discussed so far. A cistern isn't actively feeding a fixed fire pump inside a building.
Right. It is a static pool of water designed specifically for municipal fire department apparatus, the fire trucks, to pull up, drop a hose, and draft from.
It is the ultimate interface point between private infrastructure and public first responders. To facilitate this interface, the standard requires a dry hydrant assembly,
Which is essentially a hard suction pipe that reaches down to the bottom of the tank and comes up to the surface with a connection manifold. A critical detail for the design engineer is that the threads on that manifold must be acceptable to the local authority, having jurisdiction, the AHJ.
This is where local codes override generic standards. If you design the system with a standard 4.5-inch national standard thread, but the local municipal fire department exclusively uses a 5-inch Stores Quick Connect coupling, the fire engine physically cannot hook up to your tank.
Your hundreds of thousands of gallons of water are completely locked away while the building burns, just because of a threading mismatch.
Coordination with the local responders is non-negotiable, but there is a pure, unyielding limitation of physics outlined in this section that is arguably the most critical number for a civil or safety engineer designing a cistern.
The depth limit.
Yes. The standard mandates that the lowest water level in the tank used for fire protection cannot be more than 15 feet below the grade level where the fire truck will be parked.
This is a phenomenal constraint. Why exactly 15 feet? Modern fire trucks are incredible pieces of machinery. They have massive multi-state centrifugal pumps capable of moving 1,500 to 2,000 gallons per minute, driven by 500 horsepower diesel engines.
They're beasts.
Why can't a pump with that much raw mechanical power pull water up from a tank buried 30 or 50 feet underground?
Because pumps do not actually pull water. Water does not have tensile strength. You cannot grab it and drag it up a hose.
Right. So what is the truck actually doing?
What the fire truck's pump actually does is evacuate the air from the hard suction hose, creating a low-pressure vacuum. Once that vacuum is established, the weight of the Earth's atmosphere pushing down on the surface of the water in the tank forces the water up into the hose to fill the void.
So the pump just creates the empty space, and atmospheric pressure does the actual heavy lifting.
Yeah.
If we look at the math, standard atmospheric pressure at sea level is roughly 14.7 pounds per square inch.
Correct.
If you have a perfect absolute vacuum, that 14.7 psi can theoretically support a column of water approximately 33.9 feet high.
That is the theoretical maximum. But fire pumps are not perfect vacuums, and real-world fluid dynamics introduce massive penalties.
Like what?
Well, you have severe friction losses as the water moves up the hard suction hose. You have mechanical efficiency losses in the pump casing. And crucially, you have the vapor pressure of water.
Vapor pressure.
If you ask a fire truck to draft water from a depth greater than 15 feet, the vacuum required becomes so deep that it drops below the vapor pressure of the water at ambient temperature.
The water inside the suction hose will literally boil into vapor without any heat being applied,
And the pump will cavitate on the vapor it just created.
which destroys the pump, like we talked about earlier.
Exactly.
Yeah.
It physically cannot lift the liquid water any higher. The physics simply break down. If an engineer decides to bury a cistern 20 feet underground to save surface space or avoid frost lines, the bottom 5 feet of that water is forever physically inaccessible to a fire truck.
It's phantom capacity. The 15-foot rule ensures the water remains within the strict physical limits of atmospheric drafting. The laws of physics dictate the civil engineering.
They always do.
Finally, let's discuss the valving on elevated tanks. Section 14.2.11 mandates that check valves must be placed horizontally in a pit underneath the tank or safely protected on the ground floor. They cannot be installed vertically in the riser pipe 50 or 100 feet in the air.
That rule is driven entirely by maintenance safety and hydrostatic head pressure. A check valve for a large fire main is a massive, heavy mechanical device containing a large metal clapper assembly designed to prevent water from flowing backward.
It requires regular inspection and maintenance.
And the hydrostatic pressure inside that vertical pipe is immense. If the tank is 100 feet in the air, you have roughly 43 psi of static head pressure bearing down on that valve, plus the raw weight of the water column.
If a maintenance crew needs to service that valve, they cannot safely unbolt a 500-pound piece of cast iron while suspended on scaffolding 50 feet in the air, especially while fighting the static pressure of a fully loaded pipe.
Putting the valve horizontally in a frost-proof pit at our base ensures it can be safely isolated with control valves, completely drained, and serviced by technicians standing safely on the ground.
Accessibility equals maintainability. If a critical component is dangerous or exceedingly difficult to reach, human nature dictates it simply won't get maintained. The NFPA writes maintenance accessibility directly into the design constraints.
Which is how you guarantee the system will actually work when it's called upon decades later.
Let's unpack everything we've analyzed today and synthesize the core takeaway for the safety engineers listening. If we look at the totality of the 2023 edition of NFPA 22, the prevailing theme is a fundamental shift in perspective. A water tank is not a static architectural feature.
It is not just a concrete box or a steel bucket sitting dormant on a hill.
It is a highly dynamic, rigorously engineered machine. It must manage complex thermal loads, resist extreme structural forces, control violent fluid dynamics, and mitigate biological and chemical decay.
It may sit completely silent for 30 years, but it must spring into flawless mechanical action in milliseconds the moment a valve opens.
Every single nuanced code requirement we've discussed today, the 48-inch vortex plate hovering exactly 6 inches off the floor to break the velocity gradient, the 4 elbow swing joints utilizing geometry to absorb thermal expansion, the raised metal arrow ensuring half a century of pneumatic accuracy, the 15-foot depth limit dictated by atmospheric pressure, every one of those rules is written in the ink of past failures.
Someone, somewhere, lost a facility because a pipe froze, a pump cavitated, or an engineer misunderstood Boyle's law. The code is a collection of hard-won physical truths designed to prevent those failures from ever repeating.
And that leads to a profound realization about the safety engineering profession. We are constantly adjusting our mathematical models based on a rapidly changing physical reality.
And that reality is shifting faster than ever.
Which leaves us with a final provocative thought to ponder as you go back to your CAD drawings and hydraulic calculations. We discussed how the 2023 edition completely removed the historical lowest one-day mean temperature map in favor of dynamic, real-time thermal calculations.
Right.
As climate change continues to shift extreme weather patterns, bringing crippling week-long deep freezes to traditionally warm southern states and extreme prolonged heat waves to northern regions, how will the design of these completely passive tanks need to evolve over the next 20 years?
It's a huge unknown.
If the NFPA committee had to throw out the historical temperature map because the climate simply outgrew it, what structural, material, or environmental assumptions are we making in our engineering models today that the reality of the environment will prove completely dangerously wrong tomorrow?